Welcome to AP Biology. I want to talk today a little bit about solute concentrations and then we'll get into pH a little bit. So a solute is something that's dissolved in a liquid, and the liquid for us is water because every living thing on this planet at least has water inside of it, and a lot of living things live in water too. So our cells actually have water inside them, and then they're bathed in tissue fluid. So water's all around our cells, and water is inside our cells. For every organism, they all have water at least inside their cells. So living things are made out of water, and then other stuff dissolved in it. So we need to know sometimes how much dissolved stuff there is inside of a cell, or maybe inside of the water here that something is living in. Or we might want to know how much medicine to give to a person. And so we might want to know the amount of stuff there is that's going to get dissolved in a water. So I'm going to talk a little bit about quantifying that number, putting a certain number with it. All right. So I want to get at the idea of molarity because molarity comes up all the time in AP Bio. So I want to sort of show you how we get to that. But at the end of all of that discussion, if you just understand that molarity is a concentration, a certain amount of stuff per liter, per stuff dissolved in water, that's what I really want to get at. The stuff that I'm going to talk about now, if you haven't taken chemistry yet, if you're just taking it this year, it might seem like, there's a lot going on, but it's stuff that you'll go over again when you get into this unit in chemistry. Okay, so I'm going to start with the definition of molecular mass. That's the sum of all the masses of all the atoms in a molecule. So for example, here's sucrose, C6H12O11. That means that there are 12 carbons in sucrose, there are 22 hydrogens in sucrose, and 11 oxygens in sucrose. Each carbon atom has 6 protons, and usually there are 6 neutrons too. So carbon has 12.011 atomic mass units, I think. We're going to go with 12. It's easier. So that means it's sort of like the mass of 12 protons and neutrons together. So if we have 12 of these atoms, and each atom has 12 atomic mass units, 12 things that weigh the same as a proton or neutron, we would do 12 times 12 for the mass of the carbons, of all the carbons in the sucrose, in the sucrose molecule. Hydrogen has 1 atomic mass unit. Usually there's just 1 proton. Occasionally there's a neutron or 2, but for the most part, hydrogen weighs 1 atomic mass unit because it has 1 proton. We have 22 of those, so it would be, for hydrogen's contribution, 22 times 1. And then for oxygen, oxygen has a mass of 16 atomic mass units. I think it's like 15.99 something something. Anyway, there are 11 oxygens, and each oxygen has 16 atomic mass units because it's got 8 protons and 8 neutrons, so 16 times 11. So the mass of sucrose is going to be 12 times 12, 22 times 1, and 11 times 16. And when we do all that, we get 342 atomic mass units. It's equivalent to the mass of all the protons and neutrons because the electrons hardly weigh anything in an atom. All right, this is a really, really cute little animal called a mole. Isn't it adorable? And so now I want to define what a mole is. And it's not, for chemistry, it's not this really cute animal, sadly. So if I have a small jar of sucrose and I give it to you and I show you where the scales are and I say, can you please weigh out 20 molecules of sucrose for me? I'd like to do a chemical reaction with it or whatever. You would be like, sorry, molecules are too small to weigh. I can't do that. And so instead, I'm going to have you weigh moles. So what is a mole? So it's not this. This is a dozen eggs. But a dozen, if I tell you eggs are a little boring, what if I tell you I'm going to go buy you a dozen donuts? Yay, that means 12. So you probably know that a dozen means 12. A mole is just like that, except it's a much, much bigger number. 6.02 times 10 to the 23rd things. Usually we're talking about molecules, but that's 6 with 23 zeros after it. It's a lot. It's a big, big number. And so that's a number that I can sort of weigh out in the lab because that's a whole lot of molecules. So there are 6.02 times 10 to the 23rd, that same number, atoms, or atomic mass units in 1 gram of a substance, and that's due to the way that the gram was originally defined. So for sucrose, 1 mole of sucrose weighs 342 grams because there are 342 atomic mass units in it, and that's the way it was defined. You can weigh out 342 grams of sucrose. That's easy. All right, yay. So that's what a mole is. I don't care if you memorize that number for me. You'll need it for chemistry. But if you know that a mole is like a big number, a whole lot of molecules, that probably works pretty well. Molarity, though, this is what I really do want you to know. So for aqueous solutions, we talk about the number of moles of something in 1 liter of water. This is called molarity, and we give it the capital M. So if I tell you that there's a 2 molar solution, that doesn't have as much stuff in it as a 3 molar solution, right? And actually, you've already seen some graphs where it said like 0 to maybe 10, I might have said micromolar, right? And then 20 micromolar. So that means a concentration. So when we look at the number of something per liter, that's a concentration. It's the amount of stuff dissolved in a certain amount of water. So if all you get out of all of this is that molarity means a certain concentration of stuff in water for our case, that's what I want you to get. Okay, I wrote all over this. So 1 mole of sucrose, 342 grams, which you can weigh out in the lab, dissolved in a liter of water would be a 1 molar solution. Twice that many grams would be a 2 molar solution, etc. All right, chemical reactions. So you probably remember that the things you start with are called reactants and the things you end with are called products. This is showing you that the reaction can go both ways. So it goes this way and then maybe it goes back the other way and the reactants become the products, etc. So that's sort of what I asked here. So this reaction is reversible, meaning it can go both ways because there's an arrow going both ways here. All right, so I want to talk about acids and bases a little bit, but before I do that, we sort of need to talk about this picture. So let's draw that out a little bit, I think. All right. Okay, so water. Remember, water has water is made out of oxygen and hydrogen, right? And so oxygen has 8 protons, and so that means it's going to have 8 electrons. 1, 2, 3, 4, 5, 6, and then we'll double them up, 7, 8. So that's oxygen. And then hydrogen is going to have 1 proton with 1 electron, and they'll share these, and 1 proton here and 1 electron, and they'll share those two. So that's my, my water, which maybe I could draw like this if I wanted to. Anyway, once in a great while, not very often, water will spontaneously break apart. And so what happens is that the hydrogen will come off. So remember how oxygen has 8 protons and they hold those electrons in this first and second energy level. They hold the electrons in very tightly. Oxygen is very electronegative. So rarely, but occasionally, the positive, the proton, the hydrogen comes off. And when it does, it leaves behind its electron, usually because the electron is really attracted to the hydrogen instead. And so this thing, we're going to call it an ion. So this is a hydrogen ion. An ion is any charged particle, either positive or negative. So the crazy thing here with this, it's also just a proton, right? That's all it is here by itself. That's kind of cool, right? Whereas other ions have, electrons and protons. But okay, and then I have this part that's left over. So I'm going to write and, too many pluses here. I've got 8 protons in my oxygen. Here's the electrons. Oops, I'm in my own way. Let's see. So 1, 2, 3, 4, 5, 6. I'm going to do 7, 8 here. We'll pretend it turned a little because I have the word and there. It's in the way. So this one I'm just going to draw right here. All right. So notice that this electron stayed put with this one. And I hope that makes sense. And so now I've got 8, 9 positives, but I've got 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 negatives, right? So I have an ion here too. So this is called the hydroxide ion, and I'm going to write it like this, OH minus, because there's an O and an H, right? And it's got a negative charge because there's more negatives here than positives. I hope that wasn't confusing. This I drew down, like I sort of, like it's this way because I wrote the word and there and it's in my way. I hope that sort of makes sense. Anyway, so what you have here is the dissociation of water. Water has broken apart into the hydrogen ion and the hydroxide ion. Now, really, it doesn't really stay like this. Most of the time, this gets taken up by another water molecule. So what it'll look like is the 8 pluses from oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This is oxygen, right? And it's already, if it's in a water molecule, let me get me out of the way. If it's in a water molecule, it'll have the hydrogen here, and so they'll be sharing here, and it'll have another one here, and so they'll be sharing. So this is just a plain old water molecule, right? But if this proton comes over here and says, "Ah, come on, let me share too," then what you have is H3O, and you've got now an extra proton on it, right? Because before it had been neutral, but now it has 8, 9, 10, right? 10 protons, but it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Electrons, oops, I forgot 8, 9, 10, 11. It's got 11 pluses because it's got that extra one here. So overall, it's positive. This is called the hydronium ion. All right, so really, instead of existing like this, it usually exists more like this, but I'm just going to probably talk about this just to make life easier. Yay? Okay, so water dissociates very rarely, about 1 times 10 to the negative 7th molar. That's the concentration of these, or if you want to call it these, in pure water. So you get just a tiny little bit of that hydrogen ion in water. 7, that's a funny number, but that's what it is, 1 times 10 to the negative 7. So that's what I'm trying to show here. So in pure water, very rarely, a hydrogen ion is transferred from one molecule to another, resulting in these two ions of opposite charge. You've got the hydroxide ion that's negative and the hydronium ion that's positive. I'll usually just write this as an H plus, as just a hydrogen ion, just for ease. Okay, so we'll call them H plus and OH, but really they're usually H3O and OH. Okay, so this happens in pure water so rarely that the concentration of hydrogen ion, this one, is 1 times 10 to the negative 7th, which is why, whoops, so the hydrogen ion, and actually the hydroxide ion too, is 1 times 10 to the negative 7th. And that's how we define the pH scale. So that is pH 7, and the number comes from this. So it's the concentration of these. And actually these, but only by accident, only because there's just as many. Okay, so definition of acids. Acids are any substances that release hydrogen ions when they're in water. So this is hydrochloric acid, but I wouldn't expect you to know that necessarily. But if I show you the whole reaction, you can see that the hydrogen ion is released right here. And so therefore, I would want you to know that this thing must be an acid. A base is going to be anything that reduces hydrogen ions. There are different ways to define base, but that's what I'm going to go with. And so often that's an OH. So this is sodium hydroxide, a base, and I wouldn't necessarily expect you to know that, but if it releases OH, that can join with an H and get rid of the H, so it will decrease hydrogen ions. So an acid releases hydrogens and a base often releases OHs. What happens when those go together? Well, I've got an H and I've got an OH. So I've got two H's and one O. Oh my God, that's water. Pretty cool, right? That's a neutral water molecule. So acids and bases can neutralize each other. When I say neutralize, be a little bit careful because sometimes when I say something's neutral, like protons and neutrons, if you have the same number in an atom, then they're a neutral atom, right? Now I'm using the word neutral to mean you're not acidic or basic, so same word, kind of different meaning. All right, so hydrogen ions and hydroxide ions come together and make water totally neutral. Kind of cool. So pH is the negative logarithm of the hydrogen ion concentration. So pH equals the negative log of the hydrogen ion concentration. So if your hydrogen ion concentration is 1 times 10 to the negative 7th, then the negative log of that is 7. So water has a pH of 7 if it's totally neutral water, right? So as this number gets bigger, the to the negative part is smaller, right? So 1 times 10 to the negative 6. I don't know if I think I said that backwards. 1 times 10 to the negative 6th is a bigger number than 1 times 10 to the negative 7th, even this, right? Because it's negative. Does that make sense? So pH 6 actually has a bigger concentration of hydrogen ions. pH 2, 1 times 10 to the negative 2, that's a much bigger number than 1 times 10 to the negative 7th, right? This is 0.1234567. That's that number. That's the concentration of hydrogen ions when you have a pH of 7. When you have a pH of 2, you are at, what is it? 1, right? Because that's 1, that's 2. Yeah, that's, oops, 1 times 10 to the negative 2, sorry, because you go over 1, 2, right? So this concentration of hydrogen ions, that's a lot of hydrogen ions. So pH 2 has many, many more, many orders of magnitude more hydrogen ions than a pH 7. Okay, so the pH scale, let me get rid of all this writing. pH, oops, now I've gotten rid of everything. So the pH scale goes 0 to 14. Neutral is at 7. Acids are anything less than 7, and bases are anything greater than 7. And so I usually, if you forget that, I usually tell my kids to draw a scale from 0 to 14 with 7 in the middle, and then you sing the alphabet song, A, B, and then you're done. So acids are less than 7 and bases are greater than 7. The only time this breaks down is when you realize that bases are also called alkaline. Awesome, right? Okay, so the lower the pH, the stronger the acid. So what does that mean? If you have a scale from 0 to 14, here's 7. All of these are acids, right? Here are the acids. But if you have something, a solution that is pH like 6.5, let's say, that's really close to 7. That is not a very strong acid. It's almost neutral, right? So this is going to be a weak acid, right? And then something way far away from neutral, right? pH 7 is neutral. So something way over here like pH 1, well, that's a very strong acid. Yay? So the lower the pH down here at 1, the stronger the acid. Kind of tricky. The bases are over here. And so pH, let's say pH 8, oops, pH 8 is going to be a relatively weak base, but pH 14 would be a very strong base. So you have your strong ones out on the ends. They're very, very, like have a whole lot of hydrogen ions or a whole lot of hydroxide ions, or at least very, very few hydrogen ions. And then the weak ones are close to pH 7. So those are acids. The higher the pH, the stronger the base, which is what we had just said over here. And those are some bases. Here's the pH scale with some common stuff that you might know, like apple juice and coffee and antacids. Okay, quiz time. Which is the strongest acid? Well, I'm going to cross these out because they're not acids. And so out of these two, I have to remember that the things closest to pH 7 are pretty weak. They're almost neutral. So that means pH 2 is my strongest acid. The weakest base, well, these aren't even bases, so I'm not going to consider them. The weakest base is going to be the one that's closest to neutral. That's pH 9. The strongest base is here, and the weakest acid is the one that's closest to pH 7, but still an acid. Awesome. Okay, finally, a buffer is a substance that minimizes changes in the concentration of hydrogen and hydroxide ions. It can accept extra hydrogens in the solution or donate hydrogens when there are not enough. So I'm going to give you an example of that. Buffers are usually made of a weak acid and a weak base, the conjugate base. So here's carbonic acid. It happens actually whenever you have carbon dioxide in water, right? So these are going to combine. H2 is this, C is this, and then O2 plus O is O3. So anyway, carbon dioxide just from cellular respiration and water come together and make carbonic acid, which can break up into the bicarbonate ion and hydrogen ion. And so here's the thing. If your blood gets too acidic, let's say I don't know, something bad is happening in your body and you get too many hydrogens, that would be too acidic, right? If you're going to have too many of these, this reversible reaction is going to go this way more and make more carbonic acid. It's going to sort of go the opposite way of what you've got. So if you have too many of these, you're going to go back that way. If you have too few, right? If you're not acidic enough, if you're too basic, so if you have too few hydrogen ions, the reaction is going to go this way and create more of them. So buffer systems in your body help to keep a balance so you don't get too acidic or too basic. Because if you get too acidic or too basic, do you remember what happens to your proteins? They unwind, right? They denature. Oh my gosh. And then once they're the wrong shape, they can't do what they're supposed to do. It's kind of rough. Okay, so chemical equilibrium is reached when the forward reaction and the reverse reaction are producing a stable concentration of each chemical. That's the end of my story.